Oh, hi. I'm just eating an ice cream cone. Actually, it's frozen yogurt, but it's still pretty good. Do you like ice cream cones? Let me ask. When you go to the ice cream cone shop, do you get one that's actually a cone? Or do you get one of those cake cones that's kind of square and like, I don't know, it tastes like cardboard and it's really flimsy? Not me. I really like a good sugar cone. In fact, not just the shape. The cone's a very fascinating shape. I like it for that reason. But also, did you know that cones, when you cut them at different angles and at different places, they can produce some other interesting shapes? Let's take a look at that. Today we're going to talk about conic sections. I'm going to put this away and hopefully it'll still be good by the time the lesson's over. All right, so I have here a plastic cone that has been cut in various areas and various shapes. And I've got a little thing here that helps me measure an angle. What's important when you're going to cut a cone is, well, let's talk about parts first. You've got the tip, the vertex, you've got the base, which is a circle, and then you've got a central axis that runs down the middle. The key thing here, the important thing, is the angle that the base makes with the side. So it's, let's see if I can get this right. It's that angle right there between the base and the side that actually is important when you cut cones. So if I cut a cone so that the angle is 0, just like parallel to the base, chop, I get that right there. That forms a circle, and it's just a little tiny cone. Maybe I could get some ice cream in there. I don't know. Anyway, if I raise the angle of the slice up a little bit, but still smaller than the angle of the base and the side, smaller than the angle in the base or the side, slice, I get this shape right here. Can you see that? That's your oval, or better term would be an ellipse. Okay. Now let's see. I want to go this way. If I cut a cone such that the slice is at an angle equal to the angle that the side makes with the base, I get this one over here. If you look at this line right here and compare it to the angle here, see if I can get that in. Do you see that they're parallel? Okay, those are parallel lines. The side and this cut right here, and that gives us, come on out of there. Oh, come on. They never come out when you want them to come out, but they come out when you don't want them to. That right there, nice, yeah? That's a parabola. You guys that have done quadratics, did you know that a parabola is what you get when you slice a cone at an angle parallel to the side? There you go, nice one. Okay, and then the last one, our angles keep getting bigger. The last one says if I cut a cone at an angle that's bigger than the angle made by the side and the base, I get this thing. This one's actually cut at a 90-degree angle. And I get, come on. I get this one right here. You may think, that looks like a parabola too. No, it's a hyperbola, which is a little bit different. In fact, if you can imagine two cones that are on top of each other with a point of one, comes down with a point of another one, if you cut this way, you're going to actually cut two shapes out. So hyperbolas have maybe two areas. But we'll talk about that a bit later. All right, so circles and ellipses, you're thinking, I've seen those before. Where have I seen those before? Probably from a geometry class, right? So if you took a Euclidean geometry class, which is plane geometry, a surface, you've talked about circles and maybe ellipses and maybe even parabolas. So let me switch over now to my document camera and let me draw a circle. All right, so I've got my sheet of paper here. I'm going to use a thumbtack to keep it down, if I can get the thumbtack to stay. Okay, so I've got a point right here, and I'm going to put another thumbtack in the center of that. That's going to be my center of the circle. And you think, oh, I've done this. He's going to draw a circle with a compass. No, I'm going to draw it with string. Say what? Yeah, that's my very low budget compass. How do you draw a circle with a piece of string? Watch. Take my green pencil, put it in here, pull it tight, and then all I have to do is go around. Voila! Look at that. See, the string controls the distance that my pencil is from the center. It keeps it always the same distance. There we go. There's your circle. And you know that every single point on the circle, say like that point right there, okay, that point right there is the same distance from the center to the circle. So the distance here to here is the same as any other point on the circle, say like from the distance from this point to that point right there. Okay, so let's give a definition then of a circle from a Euclidean geometry perspective. So let me switch over now to the iPad. We'll see if this works. Conic sections. Yes, what does that mean? That just means you're going to cut a cone. Okay, a circle, the collection of all points in a plane that are equidistant from a single point. This point's called the center. Right? You knew that. Here's our perhaps formal definition of a circle. Equidistant, which means I'm going to have something like this. The distance between a point on the circle and the center is equal to some number. Sooner or later, I'm going to have to measure that distance. What's that distance called between a point on the circle and the center? Called a radius, right? Be a radius. But now let's talk about circles historically. The ancient people believed that the Earth was at the center of the world or the solar system or the universe, the known space. And they understood that the sun and the moon and the stars went around the Earth, and guess what? In circles. Now, that was not an unreasonable assumption to make. In fact, all human experience early on indicated that no, the Earth did not move, and the sun and the moon and the stars all went around the Earth. So if you're sitting down, sit real still and tell me, do you feel the Earth moving? Probably not, unless you're in an earthquake, right? So it was natural for them to conclude that. And so the circle then had its place fundamentally as the basic shape of geometry as seen in the movements of the heavens. Copernicus in the 1600s or so came along, and Copernicus was an astronomer, and he's working with all of these very complicated calculations to figure out exactly when the planets are going to be at certain places and the moons at certain places, and eclipses that happen in certain places and so forth. It's just really complicated to keep all of this. You know, they had circles within circles, epicycles and stuff like that. Copernicus says, you know, it makes the math easier if you actually put the sun at the center and put the planets in order out from the sun, going around the sun in circles, in order of how long it takes for them to make one of their complete cycles. And the Earth was third in that list in terms of the time to make one complete cycle. And Copernicus said, you know, it just makes the numbers easier. And then there was this whole argument of, well, if the math with the sun at the center is more true, does it actually have to be physically true? Copernicus thought, yeah, but that was kind of an unpopular view. But it slowly gained traction. Okay, so after Copernicus comes along Kepler. And Kepler says, no, it's not a circle, it's an ellipse. Well, what's an ellipse? Let me switch back over to the document camera, and we will put our circle aside for a moment, and we will start out with an ellipse. If a circle has one center, guess what? An ellipse has two. You're thinking, what are you talking about? Two centers. How can something have two centers? Well, okay. So let me show you. I got my 2 points here. These are my two centers. They're called foci or focus points, plural of focus is foci, foci, focuses. Anyway, now I've got a very special tool that I'm going to use to draw the ellipse. More string. String's great, yeah. Okay, so watch what happens here. All right, so I'm going to put my string around both centers, as it were. I'm going to take my pencil and I'm going to pull it tight, and I'm going to let the string now determine where the pencil goes, and watch this. Look at that. Look. Isn't that nifty? Check that out. The string between the blue dots remains the same length, but the length of string that goes to the pencil changes. But it's always the same overall distance. The distance from here to here compared to the distance from there to there changes, but the sum is the same. When you add those two distances together, you always get the same number. What are you talking about? Well, let's pick this point then right there. And let me remove the string and remove the thumbtacks. This point right here. Okay, so if I measure the distance from the point on the ellipse to the first center, and then measure the distance from a point on the ellipse, whoops, slipped a little bit, to the second center. This we're going to call D1, and this we're going to call D2. If I take D1 plus D2, I get some number. And the sum, the total, doesn't change, even though the individual short little distances might change. Well, what do you mean? Well, let me pick a point. Let me pick a point way, let's say over here. Let's pick this point right there. It's really, really short now from here to that focus right here. Maybe I'll call this D3. And then it's really, really long from this point all the way over to the other one. This right here. Call that D4. Well, guess what? D3 plus D4 has to equal then the same number. Very interesting. So how do we write then a formal definition then for this? Let's switch back over to the iPad. An ellipse, the collection of all points in a plane whose sum, which means to add them, sum of distances from two fixed points is a constant. Curious. When we did a circle, it was a distance is equal to some number, a constant number. What do we have going on here? We have D1 plus D2. Add two distances together. Then you get a number. That's neat. And so let's talk now about Kepler. Kepler read Copernicus's work and thought, I think he's right. I think it is true that the sun is at the center, and the math works, and I'm convinced that it's physically true in you know, like the physical world, it's real space. But he still wasn't satisfied with the math. And so he worked and worked and worked on the math, and he had access to Tycho Brahe's meticulous recordings of observations, and he spent years on this. And he finally comes down and he says, I found a way for the math to work. It's not a circle anymore, it's an ellipse. Kepler said that the planets revolve around the sun in ellipses with the sun at one focus. The sun is going to be at the location where one of those center points is. And then the planets go around in ellipses. My question's been, what's at the other focal point? Like, nothing. Like, shouldn't there be something there? I don't know. That bothers me just a little bit. But it wasn't an ellipse like the one that I drew, which was really exaggerated. The ellipses of the planetary orbits around the sun are so closely matched with the circle that it's very hard to tell the difference. Even the most outrageously elliptical orbit, which is what, Pluto, Neptune, something like that, it's very nearly a circle. So it wasn't unreasonable for Copernicus to say, it looks like a circle to me. The math works for a circle. Kepler comes along and says, the math isn't as nice as I want it to be. Like, it should be better than that. Like, it should work out more precisely. And so he comes along and says, oh, an ellipse. Okay. So if you cut a cone parallel to the base, you get a circle. If you cut a cone at an angle less than the angle of the side, you get an ellipse. What was the next one? A parabola. What's a parabola? Well, let me switch back over to the document camera. Get rid of Mr. Ellipse. And I'm going to cheat. I have pre-drawn a parabola. In fact, if you've done quadratics, say in algebra class, this red shape here should look familiar to you. You're like, oh yeah, I've seen those before. But what's with that blue point and that blue line? Wow. Yeah. A parabola is this. A parabola is a collection of all points, like this one here, that are the same distance from a line, the blue line there, and a fixed point that's not on the line. What do you mean? The distance from the parabola point to the focus point is the same as the distance from the parabola point to the line. So let's double check. I picked an easy one right here because I can just count the grid squares. So let's check. How far away is this parabola point from the focus point? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 units. And then I have to go from this parabola point down to the line. And remember that the shortest distance between a point not on a line and a line is the perpendicular to that line. So I have to come straight down. 1, 2, 3, 4, 5, 6, 7, 8. Hey, it works. So this point is on the parabola. All of these points now, if you take the measurement of any point on the parabola to the focus point and then to the line, it's the same number. It's not a constant number. The distances are constantly changing, but they're always the same between the parabola point and the focal point and the parabola point and the line. Another easy one is this one right here, right? Remember that one? That's the vertex. So let's check up to the point. 1, 2, 3, 4. 4 units from the vertex to the focal point. And then down, 1, 2, 3, 4, 4 units from the vertex to the line. Even this one over here, if you take the distance between this parabola point and the focal point, this distance here must be identical exactly the distance down to the line. Okay, nifty. So let's see if we can get now a definition of that. The collection of all points in a plane equidistant. Kind of like a circle, from a line and a point not on the line. And so we've now seen circles in the physical world through maybe the sun and the moon and the stars, and then maybe even ellipses, parabolas. The ancient Greeks knew about the parabolas, of course, by this definition and by cutting a cone. But where do you see it in the natural world or the physical world? It wasn't until Galileo that somebody said, hey, we see a parabola in this situation. Galileo said that projectiles, like an arrow or a cannonball or a thrown rock or something like that, projectiles follow a parabolic path. Obviously, the ancients knew that it was a curved path, but like Aristotle thought it was a semicircle. Galileo says, no, it's a parabola, and it depends on at the angle at which you throw it. Okay, so projectiles follow a parabolic path. Other places where you might see parabolas would be in light reflectors, like the headlight assembly of your car or flashlight. If you put the light source at the focus and have the mirrored surface be the parabola, any light that hits the mirror is going to go out straight, and vice versa. Anything that comes in will be reflected up to the focal point. So like if you've got satellite dishes that have like a dish, a little bowl, and then there's like a box that's right up there. That box is at the focus. That's collecting the radio waves, the unseen light waves that bounce up then to that location. Okay, so we've got a circle, an ellipse, a parabola. The last one is probably the challenging one, And I didn't draw that one either. That one is a hyperbola. Looks like that. Looks kind of like two parabolas, but it's not. I've pre-drawn this one. The red part here, that's the actual hyperbola. And like I said, you get two of them. Why is that? Well, again, I've got two center points, or two focus points, as it were, like an ellipse. But instead of adding them, and remember, like an ellipse was curved in on itself when you went around these, a hyperbola is curved outward, curved away from them. So we're subtracting the two distances. So if I take the distance from P to G, the longer one, and subtract it from the distance from P to F, the distance from a point on the parabola to this focus and the distance from a point on the parabola to this focus, if I do the subtraction here, I have to get a constant number. It's always got to be the same number when you do the subtraction. And it's going to have to be maybe the absolute value, because you can't subtract a larger number from a smaller number and wind up with a negative, because it's a distance, and distances have to be non-negative. So anyway, we'll get into more into hyperbolas in a bit, but let's give the definition for them now. Okay, the collection of all points in a plane whose difference, which means subtraction, of distances from two fixed points is a constant. All right, now where do you see this? Well, this one's kind of hard. Maybe comets. It's funny, a lot of these are astronomical, but comets will come in and then go around the sun and then head back out. Comets that don't come back. Obviously, Halley's Comet comes back, so it must be an ellipse. It's got like a long kind of thing. But some comets come in, they get caught in the gravitational field, and they go out, and then they never come back, and so it's one side of hyperbola. Another place you might see it is actually in a saddle. If you've ever ridden a horse, you know that around the sides of the horse, the saddle curves down, but around the neck and the rear end, the saddle curves up. So this is a curvature in one axis going one direction, and a curvature in another axis going another direction, so maybe a saddle. Okay, you're saying, gee whiz, like you've talked about equations a lot. Yeah, this one's going to be distance 1 minus distance 2 is equal to a number. Right? Did we do the one for the parabola? We didn't do the one for the parabola. The parabola says the distance from one side has to be equal to the distance from the other side. The distance from the parabola point to the focus is equal to the distance from the parabola point to the line. All of these distances, how are you going to measure distances? Well, you can do it with a ruler, right? 3.4 centimeters or something like that. But wait, how would you set up these equations if you don't know what the numbers are? You would say, wait a minute, that's like impossible. No, that's algebra. Right? Algebra is mathematics of unknown numbers. What kind of method are we going to use to do that? Where's our method? Well, we have to talk about the guy that developed the method, capital M. Who developed the method of doing geometric distances without knowing what the numbers are? Monsieur René Descartes, French philosopher, mathematician, 1600s or so. Maybe you're familiar with his very famous phrase, I think, therefore I am. But here's what René Descartes did. He was very interested in mathematics. He said mathematics gives us certainty. Because the truths of mathematics are certain truths. There's no guess, there's no maybe, there's no perhaps. It's certain. And it can be demonstrated. He said, wow, what if we can take these things of mathematics and then use them in other areas? Can we take some rules of mathematics and put them into some other areas? And maybe find out some truth there as well? Can we be certain about other things like ethics or politics or law or other things like that? And so he developed his mathematical method of discovering truth, and he wrote a book called Discourse on the Method. And so you should read it. I had heard this phrase here a lot from people, and people told me that he meant different things. And I finally sat down one time and read Descartes, or I read Discourse on Method. It's a really good book. You should read it. You may not be able to understand all of it, like I'm not sure I do, or maybe anybody does, but you should read it because you can understand some of it, and the some of it is good. And I finally got to the part where he talks about I think, therefore I am. And here's what he did. So he gives his method, he just explains his method, and naturally someone might say, well, can you give us an example of how you would use it? And so he says, I'm going to give you an example of how I would use this. And he doesn't give a small example. He doesn't give a medium example. He doesn't even give a big, like, important example. Descartes goes for the most ultimate thing that you could do with this method. What's the most important question maybe that mankind's ever wrestled with that he's not certain about? And if we could use his method and give certainty, then like we'd have it. Does God exist? Descartes' I think, therefore I am is his first statement in a mathematical proof for the existence of God. It's a nice bit of argumentation. You should read it. I think you'd enjoy it. But what he says is this. When he says, I think, therefore I am, what he's saying is that I know that I'm thinking, obviously because I'm thinking about thinking, right? So if I'm doing the thinking, I know for certain that at least I exist, right? I think, therefore I exist. And that's his first step. And then he uses his mathematical reasoning method to then come to the conclusion that God must also exist and have these characteristics and things like that. So you should read maybe some discourse. I need to do a video series on discourse on method. Anyway. But what he did was this. The first bit of success that he had, where he took algebra and he took geometry and he synthesized them together into what's commonly called now analytic geometry. All right? So algebra is like mathematics of unknown numbers, which is kind of an extension from arithmetic. And if you remember the poster behind me, arithmetic is the first mathematical art. And then geometry is like space and size, and they're kind of not the same thing. And what Descartes did is he took the tools of algebra and he put them on geometry to figure out geometry's existing problems. And in a matter of weeks, he was able to give answers to questions that had stumped geometers for hundreds, if not thousands of years. Very quickly, he's able to use algebra on the geometry. And then he used geometry, kind of the tools of geometry, on the algebra. And he's able to make great advances in algebra. And he puts these two things together. He synthesizes them. If you're in an Algebra 2 class, maybe your parents didn't take Algebra 2, or maybe your grandparents didn't take Algebra 2. I bet they took a class called Analytic Geometry. Analytic geometry was this algebra 1 and then geometry and then the merging of them together into algebra 2, which was analytic geometry. And the very first thing that he did, he's got to describe distance, right? This is a thing on distance. He's got to describe how he's going to measure distance. And so he sets up a system called rectangular space, or it's called Cartesian space because it's named after him. And they are perpendicular number lines, and you've probably been doing this for quite a long time and were unaware of it. You can use it for 2 space or you can use it for 3 space. So let me go back now to the document camera and let me find, where are we at? Let's get the circle. Okay, I drew it on graph paper. That's Cartesian space. Because what he says is this. He says if I take a number line, say like this, that's horizontal, I can now give it an algebraic name. I'll call that the x. And I'll make this maybe right here the 0 point. So this is like 1, and this is 2, and this 1. This is -3 back there. You're familiar with the number line? Yeah? And he says, but I'm going to do another number line at a right angle to it. And I'm going to do this number line. And I'm going to call this a different thing. Call that the y-axis. Whoops, can't see it. Call that the y-axis. And of course this is 1 and 2 and so forth. And this is now -3. And so he said, any point now that's on the circle, we can describe it by an ordered pair. It's an x value and a y value combined like that. That's a location. He's got to first define what a location is in his space, algebraically. Algebra defining a space, right, or a point, a location. And then he says the center here, I'm going to call that H and K. And what I have to do is I have to find the distance between a point on the circle called XY and the center HK. Does any of this sound like familiar to you? You're like, wait a second, I've been doing this for a while. And it's like, yeah, it's Rene Descartes' invention. And you can do three space. You can do a z-axis that comes out of the page, right? So that's Cartesian or rectangular space. And so now what he's going to do is he's got to figure out this distance, right, which we said before, that's the radius. And how's he going to do that? That's the subject then for another lesson. But here's what I want to talk about. This is good stuff. Descartes was able to combine two disciplines into a new, powerful one. And so I have a question for you. Why are you studying mathematics? Some of you are going to say, because I have to. Okay. Well, here's my thought for you. All right. So one of these days, you may be a specialist, and maybe it's probably not in mathematics. If you've been well educated, you may one day be a specialist. You may be an expert in your field, but you should be able to understand anything important that's said in any other field. And you should be able to use the tools and the insights of that other field to help shine light and to give you a greater understanding of your own. So if maybe you'll be a professional mathematician, maybe not. Okay? That's why poets should wrestle with mathematics, and future mathematicians should also wrestle with poetry, right? It's good. It helps us understand all the different ways of knowing. One of the saddest things is somebody who's an expert in one field but has no understanding of anything else in any other field. It's really kind of sad. But what I want to do is leave you with a quote. Where's my book? Oh, here it is. Here's my Discourse on Method book. And I'm going to get in here and real tight and see if I can show you this quote from Descartes. Let's see if I can focus on that there. Oh, down even farther. Let's see. Okay, focus. Right here, there we go. And I always had an excessive desire to learn to distinguish the true from the false in order to see clearly in my actions and to walk with confidence in this life. That's great stuff. So, my thought for you, pursue truth. And mathematics is one way of knowing truth. Are there other ways? Yeah. Can mathematics discover all truth? No. What are the other ways, and where are the boundaries of mathematics, and where does something else take over? It's good to study these things. Okay. Pursue truth. Have a great day.